Today we will be discussing some of the biomechanics at play when kicking a soccer ball. We will use torque properties, joint kinematics, and the laws of projectile motion to provide a basic analysis of the foot used to make a most excellent soccer kick. These principles help us to understand the resultant trajectory of the ball.
To begin this analysis, we must define torque. It is the capability of any force acting on a segment to produce rotation. The total torque acting about a segment is equal to the sum of the moments, where one moment is equal to external force times a moment arm. In the following video clip of a super intense slow motion soccer kick, we will analyze the torques at the ankle joint as well as the forces acting on the foot itself. Created about the ankle joint as well as the force reaction pair created between the forefoot and the soccer ball itself. A few assumptions are needed to solve for torque, including the weight of the ball diameter, mass of the foot, length of the foot, the linear accelerations, and foot angular acceleration. Many of these measurements can be obtained from MaxTrack software.
The first step in calculating torque is drawing the free body and kinetic diagrams. A free body diagram only includes the external forces acting on the system. The kinetic diagram shows the forces causing the motion of the segment. Now we are ready to start the problem. First, we find the moment arm of each force. This is the perpendicular distance from the axis of rotation to the force. Next, we set the sum of the moments in motion equal to the sum of the torques. These equations can be used to solve for the force of the tibialis anterior muscle acting on the foot. Note that the clockwise foot rotation is positive.
Using the tibialis anterior force, we can figure out the joint reaction force at the ankle, which is the sum of its force components equal to mass times linear accelerations. To determine the necessary x and y force components of the ankle joint, we assume the ball was kicked at a 45-degree angle and that the muscle is inserted at angle theta. All the force components in the free body diagram are separated into their appropriate directions and set equal to mass times acceleration to solve for the x and y joint reaction forces. Pythagorean theorem is then used to find the joint reaction force magnitude, and the inverse tangent of the components tells us the final direction of the force.
But what the force does this mean? It means that different torques and force directions acting on the foot can cause different ankle joint reaction forces and consequently influence the trajectory of the ball. Using the takeoff velocity and the initial trajectory angle, we can predict the horizontal distance of the ball. Let's do a problem. Recalling the principles of projectile motion, we know that the acceleration in the y direction is equal to gravity. The velocity in the x direction is constant, thus the acceleration in the x direction is 0. The total time traveled is equal to 2 times the time to peak because the change in height is 0.
Now we'll use a sample problem where the ball is kicked at a takeoff velocity of 17 meters per second at a 45-degree angle. As depicted in picture 2, the takeoff velocities in the x and y direction are 12.02 meters per second. First, we need the total flight time of the ball. Using VF equals VI plus AT, we found the time that it took the ball to reach peak height and multiplied that by 2 to get a total flight time of 2.45 seconds. The total distance traveled is 29.46 meters or 88 feet.
Now let's imagine that a worse player approached the ball with the same velocity of 17 meters per second, but instead kicked the ball at a 30-degree angle. In this case, the ball would travel 14.71 meters, only half the distance of the ball kicked at 45 degrees. We see that by changing the trajectory angle, there's a change in the x and y distribution of the ball force. This changes the torque magnitude and also the direction of the joint reaction force application. Thus, a different trajectory angle of the ball has an effect on the forces acting at the joint. Now we know how torque and joint kinematics influence the projectile motion of a soccer ball. Thank you for listening, and remember to kick your soccer ball at a 45-degree angle.